Topic 3.12 is called equivalent representations of trig functions. We're going to be rewriting different trig expressions and functions using different identities to simplify or to verify different proofs for trig functions. Now that means that we need to remember or learn a whole bunch of identities that allow us to change trig functions from one type to another. You learned about these last class, the reciprocal identities, and I've got them all listed here. Sine of theta has a reciprocal function, and that reciprocal function is cosecant, which means if you do 1 divided by cosecant of theta, that's actually equal to sine of theta. So we can go back and forth between sines and cosecants by making them fractions with the cosecant in the denominator. And vice versa. If you have a cosecant function, it is 1 over sine of theta. So we can go back and forth with these reciprocal identities. Same thing for cosine and secant. Same thing for tangent and cotangent. We've also learned throughout the lessons that we've had that we have quotient identities for tangent and cotangent. Tangent is sine divided by cosine. So anytime you see a tangent, you can rewrite it as sine divided by cosine. Vice versa for cotangent, since it's the reciprocal of tangent, you just flip this fraction over, meaning it's cosine over sine. But then we have what are called the Pythagorean identities, and I've only listed one of them out for you because we're going to derive the other two. Derive means to use one formula to create another. It's a big thing in advanced maths. The Pythagorean identity that we're going to talk about today and transform is sine squared of theta plus cosine squared of theta equal to 1, which means when we're solving problems, if we see sine squared of theta plus cosine squared of theta, we can just take that entire bit and change it to the number 1. Which simplifies a lot of problems for us. But that leaves out tangent, secant, cotangent, and cosecant. So we have to rewrite this Pythagorean identity in terms of those functions. So here's what we're going to do. I would use some nice small handwriting if I were you, because this is like a formula chart for you. Let's rewrite down sine squared of theta plus cosine squared of theta equal to 1, and we're going to change it. We're going to change it by dividing every single term in this function by sine squared of theta. So if I take this number and I divide by sine squared of theta, and I take this term and I divide by sine squared of theta, and I take this term and I divide by sine squared of theta, I can use some of the identities from the two boxes above this to change these values into a different trig function. So simply, we'll just do the simple part first. Sine squared over sine squared, what happens there? They cancel out, and that whole fraction becomes what? 1. All right, so that first fraction becomes 1. That's much simpler. Love that. Then I have cosine squared of theta over sine squared of theta. Does this cosine over sine look familiar? Yeah, look at the box above it. What is also cosine over sine? Cotangent. So this I can rewrite as cotangent squared of theta. I've used the quotient identity to rewrite that into something simpler. And what about 1 over sine squared of theta? Does that look familiar? What is that? What is 1 over sine squared of theta? Cosecant. So this can be changed into cosecant squared of theta. Here is our second Pythagorean identity. Let's go ahead and put we'll put like a little bubble cloud around the important ones. Here's a normal Pythagorean identity. Here is the one where I have derived it for cosecant squared of theta. Let's do it again, but we're going to divide by something else this time to derive a different Pythagorean identity. If I write it down one more time, I have sine squared of theta plus cosine squared of theta equal to 1. Now I divided by sine squared last time. What do you think I could divide by this time to get a different result? Cosine. So let's divide every single term by cosine squared of theta. And then refer to the things above, the different identities we have above, to see what these simplify to. What is sine over cosine? Tangent. So that first fraction becomes tangent squared of theta. What is cosine divided by cosine? 1. And then 1 over cosine is the definition of what? Secant. So this becomes secant squared of theta. This is our third Pythagorean identity. I need you to memorize all three. Your formula quiz next time will have pretty much everything from the front of this set of notes on it. But for you, these are the three that I want you to write down, okay? But we can actually change these three that I put in the purple cloud into different versions that might be helpful to just have listed on your paper so that when you're doing your homework, you can recognize them faster. So if we just rewrite this first one, okay, I'm going to come down here and rewrite it. I'm going to, instead of solving it so it says equal 1, I want to solve it so it says equal sine squared of theta. So if I subtract cosine squared of theta from both sides, this would end up being 1 minus cosine squared of theta. This is the same equation, just rewritten so that sine is by itself. It's helpful to see that because there may be times you recognize this in a problem, 1 minus cosine squared of theta, and that means you can change this term into a simple sine squared of theta. You can also rewrite this one so cosine is by itself. So another way to write this equation or this Pythagorean identity is cosine squared of theta equal to 1 minus sine squared of theta. That's again just subtracting sine squared of theta from 1 in the purple equation. That's the three versions of the main Pythagorean identity. I'm just having them listed on your notes for you so that it's easy to notice them later when you're using this as a formula chart. We'll do the same thing for the cotangent and cosecant version, just because, again, it's easy to have these listed. Right now, it's solved for cosecant squared of theta, meaning it says equals cosecant squared of theta. If I wanted to say equals 1, I would just subtract cotangent from both sides, which means this would change to cosecant squared theta minus cotangent squared theta. It's the same equation, just rewritten, so you can see it in its various forms. Or I can take that purple equation and solve it for cotangent, which means I could have cotangent squared of theta equal to cosecant squared of theta minus 1. Those are the three versions of the middle Pythagorean identity. Again, the main ones I want you to know are the purple because the ones I'm writing in color come from the purple one. Purple is the main one. For the last Pythagorean identity using tangent and secant, if we solve this for 1 so that it says 1 equals, that means I'd subtract tangent squared from both sides. This is something you can look for in problems and just change all of that secant squared theta minus tangent squared theta to 1, simplifying it down. Or if we solve this for tangent, this would be tangent squared theta equal to secant squared theta minus 1. Those are the three versions of the third Pythagorean identity. But again, the three I need you to memorize is the ones we put a purple cloud around. Those are the ones I'm going to ask for next time on your formula quiz. Now, of course, that's not all of the identities we're going to learn. We're going to go through all of these today in these notes, but I have put them all at the front so that you only have to look at the front of your notes when you're doing your homework. You don't have to flip through it. That's like there's a formula chart essentially on the front. The next set of identities is called the sum and difference identities. Whenever you are doing a sum and difference identities, I need you to know how to read these symbols because it's very simple if we know how to read the formula. For sine of two angles that are added together, so angle A plus, angle alpha plus angle beta, since the plus sign is on top, you're going to use the top symbol in the formula. So it's sine of alpha cosine of beta plus cosine of alpha sine of beta. When you read it a second time, taking the bottom symbol, there's a minus whenever you're taking the difference of angles in sine. You will also subtract using the formula. So top goes with top, bottom goes with bottom. Does that make sense? So the formula for the sum of sines is sine of alpha cosine of beta plus cosine of alpha sine of beta. The formula for the difference is sine of alpha cosine of beta minus cosine of alpha sine of beta. Some things I notice about this that will help you differentiate it from the one we're about to go over. Sine and cosine are mixed and matched. But the signs are not mixed and matched. Plus goes with plus, minus goes with minus. Hang on to that for a second. If we look at the formula for the sum and difference of cosine, what are some things you notice is different in this formula? Yeah, pluses with minus and minuses with plus. When you are doing the sum of angles, you're actually going to subtract in the formula. When you are subtracting angles, you're actually going to add in the formula. Top goes with top, bottom goes with bottom. It's just a way to condense these into one formula if you switch the minus plus for the plus minus. What else do you notice that's maybe different from the sine to the cosine one? Yeah, with cosine, the cosines and the sines go together. So you mix and match the symbols, but you don't mix and match the equations. So there's only one thing that's mixed and matched for each formula. For sine, it's the equations, not the signs. For cosines, it's the signs, not the equations. In this class for AP Pre-Cal, we're not actually worried about the sum of tangent. So I'm not going to really spend a lot of time on this. It's just sine divided by cosine. But if you're taking calculus next year, you will need this formula. So I went ahead and put it with everything so you're not shocked that there's a tangent sum and difference formulas. But we're going to focus on sine and cosine. The last formulas is the double angle identities. So if you have sine of 2 times some number, some angle, you can use 2 times sine of alpha, cosine of alpha. And the same thing for cosine of 2 alpha, you can do cosine squared of alpha minus sine squared of alpha. Again, this means nothing to you because it's just a formula sheet right now. What we're going to do is we're going to use this formula sheet to either verify different proofs of trig functions or simplify trig functions. Okay? Now I did this on purpose. If you look at the back page of this, what does it say on the back page? I left it blank on purpose. Rip these pages apart for a second. Now you can actually use this formula chart without having to flip through your notes because I know that's super annoying. So leave the page we just filled out with the formulas face up on your desk so you know what I'm referring to while we do all of these problems. Is that cool? Fabulous. Here's the kind of question we're going to have. In example 1, it says use identities to simplify the following their expressions. We want to simplify this down to one trig function only, and we're going to be able to do that. So here's some things we can do. If we look at letter A, I like to get things in terms of sines and cosines because it's usually easier to delete things. What am I looking for? Cancel things out. So right now, I'm going to change cotangent of theta into its quotient identity, because the quotient identity for cotangent is in terms of sine and cosine. So looking at your formula chart, what is cotangent of theta defined as for its quotient identity? Oh, that's the reciprocal identity. Give me the quotient identity. Cosine over sine. Now I'm doing this on purpose. This is cosine of theta over sine of theta. We have changed the cotangent part of this function with its quotient identity so that it is in terms of sine and cosine. That's a good hint for you to get things in terms of sine and cosine. Okay, now if we remember some things about adding and subtracting fractions, because right now this part is a fraction. To add and subtract fractions, what do they have to have? Common denominator. So the denominator of this term is sine of theta, which means what do I want to make the denominator of this side? Sine of theta. So let's work on doing that. If I know I want to have a denominator of sine of theta here, because I have the denominator of sine of theta here, which, by the way, cosine times cosine is cosine squared, what would I have to multiply this guy's denominator by to make it sine of theta? Sine of theta, right? What is sine of theta times sine of theta? Sine squared of theta. Okay, cool. So we got sine squared of theta. That's just giving them a common denominator. Now that they have a common denominator, can't we just add those numerators together? Which means we have sine squared of theta plus cosine squared of theta divided by one denominator, sine of theta. Now your spidey senses probably aren't tingling yet because you've just learned about this, but that numerator should look like something on your formula chart. Find sine squared theta plus cosine squared of theta on your formula chart. What is it equal to? 1. So I can change that whole numerator into the number 1. This is 1 over sine of theta. And what is 1 over sine of theta? Cosecant. Look at that. We're done. We've changed it from that complicated thing we started with to one trig function. This is simplifying using trig identities. I think this is so fun. So even if you hate it, you have to pretend like you like it, okay? This is really fun for me. Never. Yeah. So okay, let's talk back through what we did. The very first thing I did was I used what identity? What is this one called? Quotient identity. I like to get things in terms of sine and cosine when possible so that stuff can cancel out. Nothing canceled out necessarily, but I noticed that to add these two things together, I'd have to give it a common denominator, so that's what I did. Once they have a common denominator, you add the numerators together, which, OMG, this is Pythagorean's identity. This becomes 1, and using a reciprocal identity, this becomes cosecant. This is the game we're playing today. Yes? Basically what I did, it's a great question, is I multiplied this term by sine of theta over sine of theta so that it had a denominator of sine theta. And then sine times sine is sine squared. That's just giving it a common denominator. That's what I'm doing in green. Other questions before we keep going? All right, here we go. Number B. We're going to reduce this one. We have cotangent squared of x minus cotangent squared of x times cosine squared of x. Okay, some things we can do is we can change things into terms of sine and cosine. We can factor. We can find common denominators if needed. What do you guys think we should do first here? Let me bring your attention to something that maybe we should notice. What do you notice is in the first term and in the second term? Cotangent squared of x appears in both, which means we should probably factor that guy out. So when we factor out cotangent squared of x, what's left over? It would be 1 minus cosine squared of x, but yes. Because cotangent divided by cotangent is 1. Cotangent squared times cosine squared divided by cotangent squared is just the cosine squared, canceled out. Okay. Question for you. This stuff in the parentheses, my spidey senses are going off because it's got a 1 and it's got something squared. Look at your formula chart. Try to find 1 minus cosine squared of x. What is it equal to? It's equal to sine squared of theta. So we're going to do cotangent of x times sine squared of x. That's the Pythagorean identity again. This is why I had you write them in the 3 forms so we could recognize them quickly. Now I still want to reduce this down to one trig function. So what could I do here? Yeah. Why is it 1 minus cosine squared of x? So if I'll show my work on that then. If I have cotangent squared of x minus cotangent squared of x, cosine squared of x, and I divide both of these by cotangent squared of x, because that's what I'm factoring out, these will cancel, become 1. These will cancel, but it leaves cosine squared of x. It's like factoring out a GCF. The GCF just happens to be an entire trig function that's squared. Okay, so here's some things that I'm thinking. When I kind of get stuck on these problems, again, I always think, let's just change things in terms of sine and cosine. Can I rewrite cotangent so that it is only a sine or a cosine? What's the quotient identity for cotangent? So this is cosine squared of theta, or x, over sine squared of x. And I'm going to multiply that by sine squared of x. What are we thinking? Sine squared of x cancels. There's 1 in the numerator and the denominator. So this reduces down to just cosine squared of x. Yes?
So if you factor out
This one right here? Where does this come from? So when you're factoring it out, you can't just let it disappear like I did in green. It actually goes in front of that term. So like if you think back to just some simple algebra, if you had 2x minus 4 and you factored out 2, you don't just let that go and make this x minus 2. You do put that 2 in front of it. That's the same thing I'm doing. It just happens to be an entire trig function. You're welcome. Can we try another? Okay. How about this one? We have 1 divided by tangent squared of theta plus 1. Is there something up here that's screaming to you from the formula chart? Because it should be. What is tangent squared of theta plus 1 equal to? Is that somewhere on your formula chart? It should be. So this whole bottom thing becomes secant squared of theta. That's the third Pythagorean identity that we wrote down. That's in, I believe it's in the one in the purple bubble. Well, what is 1 over secant squared of theta? What is that defined? 1 over secant is what? Cosine. So this is just cosine squared of theta as well. The end. It's 1 trig function. Simplified down. Yeah, some of them are easy. We use a Pythagorean identity and then a reciprocal identity. Last one here for this kind of problem. Cosine of theta times secant of theta minus cosine of theta. All right. So in problem B, we factored something out to be able to reduce. In this problem, factoring out didn't help us because if you notice, it's factored right now, but like that's not helpful. So instead of factoring, let's go ahead and multiply this back in and see what happens. This would become cosine of theta times secant of theta minus cosine squared of theta. So that's reverse factoring, called distribution. And here's what my spidey senses started doing. I noticed that this is minus cosine squared of theta. Is that somewhere on my formula chart, like something minus cosine squared of theta? 1 minus cosine squared of theta is going to be equal to something that reduces down. Is there a way we can make that first term equal to 1? Let's see. All right. Putting things in terms of sine and cosine. Secant is the reciprocal of cosine, is it not? So if I use the reciprocal identity for secant, what's going to happen to those two cosines? They're going to cancel each other out. What happens when they cancel out? You just have 1. So 1 minus cosine squared of theta. That's just sine squared of theta. The end. So you have to be able to utilize any part of these identities as part of the puzzle to solve the question. Now, there's not just one way to do this. I have seen all of these problems worked in many ways. They end up at the same place. The order you do the identities sometimes does not matter. Sometimes it does. It's just a puzzle. Questions about these 4 before we move on? Example 2 tells me to verify the sum of sines identity using alpha being equal to pi over 6 and beta being equal to pi over 3. So what I'm going to do is I'm going to take from my formula chart the formula for sum of sines, and instead of writing alpha and beta, I'm going to write pi over 6 and pi over 3. So that formula would look like this. Sine of alpha, pi over 6, plus beta, pi over 3, would be equal to, and then we're going to fill in the formula. From your formula chart, you see that this is sine of the alpha, which is pi over 6, times the cosine of the beta, which is pi over 3, plus cosine of the alpha times sine of beta. Do we see how I've just plugged in the A and the B, or the alpha and the beta? Okay. Now we're just verifying that this actually works, which means I'm going to work both sides at the same time. Using fraction rules, what is pi over 6 plus pi over 3? So I'm working here, just this fraction. What is pi over 6 plus pi over 3? It's a great question, Ms. Quigley. I'm so glad you asked. If we make these have the same denominator, this would be, not 6, 2 over 6, right? Which means when you add those together, 3 pi over 6, which, yes, if you're thinking about that, that's just pi over 2. And what is the sign of pi over 2? 1. So we're hoping when we do this problem that the side with all of that business happening would be equal to 1. We're verifying this identity, proving that one side is equal to the other. Well, let's fill in with some things we know. Hopefully you have not forgotten in the week I was gone. What is sine of pi over 6? 1/2. Sine of pi over 6 is 1/2. What is cosine of pi over 3? 1/2. Okay, and then I'm going to add the cosine of pi over 6, which is what?
The cosine of pi over 6 is square root of 3 over 2.
Mm-hmm. And what's the sine of pi over 3? Yeah. Oh, good. We didn't forget. It's our unit circle values, the value from the tables. It's the table that's going to show up in your quiz next time. Ah, there it is. Okay. Let's do some math. What is 1/2 times 1/2? 1/4. What is square root 3 over 2 times square root 3 over 2? The square roots will cancel because square root of 3 times square root of 3 is just 3. What is 2 times 2? That's 4. What's going to happen when you add these fractions together? You get 4 over 4, which is, we have verified this identity. Can I let you try the next one? How about I do half of the next one and you do the other half? The half that I'm going to do is the easy part, though, so you're welcome. We're going to verify the sum of cosines, so different formulas, using alpha being equal to pi over 4 and beta being equal to pi over 2. So if I'm doing the sum of cosines, that means that this is cosine of alpha plus beta. I'm going to let you fill in the entire formula without me. I'm going to help you with this side so you know what the goal is. If I were to add these two fractions together, that's like the cosine of 2 pi over 4 plus 1 pi over 4, which is 3 pi over 4. And the cosine of 3 pi over 4, if you think about it, that's pi over 4, but in the second quadrant, cosine is going to be negative in the second quadrant. So that would actually be negative square root 2 over 2. That's your goal. I need you to verify that this formula works. So you're taking the formula for sum of cosines from your formula chart page, doing exactly like we did in example 2. I'll give you some time to think. Okay, so many of you fell for my trick. Did you use the wrong formula at first? Did you use the wrong sign at first? Some of us are lying to ourselves. But when we do this, remember, cosine has a different formula from sine, which means we're going to be doing cosine of alpha, which is pi over 4, and then cosine again of beta, which is pi over 2. And then what symbol in between? What operation? Minus. Sum of cosines is a minus in the formula. So this is sine of pi over 4. Oops. And then sine of pi over 2. When we actually evaluate these, thinking about our unit circle and all of the things that we know, cosine of pi over 4 is square root of 2 over 2. The cosine of pi over 2 is 0. The sine of pi over 4 is square root 2 over 2. And the sine of pi over 2 is 1. So this first thing becomes 0. The second thing is negative square root 2 over 2. So, ta-da! We verified. So this just disappears because it's times 0. I just cut off your thinking time, right? Okay, yeah. The next identity that we're verifying, so again, we're working with the formulas to verify the different formulas. That's what we're doing right now. It says to verify the double angle identity for sine using the sum of sines identity. So here we go. We're going to verify that sine of 2 times alpha is actually what we say on our formula chart. But using the sum of sines, if we just take this, instead of being 2 times alpha to be alpha plus alpha, let's fill in the formula as if alpha is alpha and beta is alpha. So just like I did in the first problem, we'll let this be alpha and this is beta. So if we fill it in, our formula for sine, it says sine of alpha cosine of beta, oh, except that's an alpha still, plus cosine of alpha times sine of beta. Do we follow how I just filled in the formula like we did in example 2, right? It just happened to be that the angle I'm using both times is alpha. What do you notice about the first term and the second term? It's sine times cosine and then cosine times sine. Does order matter when you're multiplying? So it's like the same thing happening twice, yeah? So we could just reduce this and say this is 2 times sine of alpha cosine of alpha. Oh, snap. Look at your formula charts for the double angle identity. Isn't that exactly what's written on our formula chart for the double angle identity for sine? 2 sine of alpha cosine of alpha. So this formula works. And in fact, you don't technically have to memorize it to use it because it is just double of a sum. You've got example 5. I want you to do the same thing. You're going to verify the double angle identity for cosine using the sum of the cosine identity. So just like in example 4, we're going to do cosine of 2 alpha. Just letting the 2 cosines that we're adding together both be alpha. So following the color code I did before, alpha and beta. But by we're going to do it, I mean you're going to do it. Go and try to verify that for me, making sure it matches what is on our formula chart. So when you fill in this formula, it should look like this. Cosine alpha times cosine alpha minus sine of alpha, sine of alpha. Well, it's kind of annoying to write cosine alpha, cosine alpha. What's a way I can simplify that? Cosine squared alpha, yes. Put the square behind the letters, not behind the angle. So this is cosine squared of alpha minus sine squared of alpha. That's exactly what's on our formula chart for the double angle. So again, these 2 double angle identities actually come from the sum and difference identity, which is pretty cool. Again, I recommend still keeping that formula chart first page of these notes available for you every time you're doing one of these. But I also have put a bunch of tips for how to verify identities. These are just a general list of algebra tips for you that you might use. We've already used some of them, but this might make your life easier. Number 1, when you are verifying identity, try to go from the longer to the shorter. So one side of these equations is going to be longer than the other. Start with the longer and try to reduce it down to the shorter. Don't forget those fundamental identities. They're going to be helpful for you to rewrite. The third tip is to look for singletons, and I'm meaning there's a single trig function in the denominator. Because when there's a single trig function in the denominator, you're going to be able to cancel these guys out very quickly, and so you reduce the number of trig functions you're using. We've already seen how factoring might help, so factoring out GCFs. There's also something called separating. Now you can split a fraction through the denominator when it is only multiplication or division. So 1 over sine of x, cosine of x can be 1 over sine of x times 1 over cosine of x. So you can split them apart like that, which might make it easier for you to reduce something. We've seen this already as well. Finding a least common denominator for 2 fractions allows you to add them together. We've seen that already. You can split. This one's super important. Actually, we're gonna highlight this one for a second. You can split a fraction through the numerator when there is a plus or minus in the numerator, but not the denominator. You cannot split a fraction at a plus or a minus in a denominator. And so it is really tempting when you get going on these problems just to split a denominator in half. You can't do that. You can split a numerator. So if you look, 1 plus sine of x all divided by cosine of x can be split apart with the 1 and the sine. Both keep the same denominator. That's allowed. What's not allowed is the reverse of that. If the 1 plus sine of x is in the denominator, you cannot split it like this. Those are not equal. So don't go too fast on these. Tip number 8 is to remember that there are trig conjugates, like complex conjugates. So it's just 1 plus sine of x and 1 minus sine of x. This is super helpful, especially when you notice that one of the versions of these conjugates is in your problem. Because if you multiply by its conjugate, you're actually creating a difference of two squares factoring question. And usually that results in one of your Pythagorean identities. So when all else fails and you see something like this in the denominator or numerator of your problem, you might want to multiply by the conjugate. But like I've said all day, truly when all else fails, rewrite the trig functions in terms of sine and cosine. Most likely something will cancel when you do that. So if you're straight up stuck, that's my best tip for you right there. So in example 6, we're going to verify that cosecant squared of alpha is equal to cosecant of alpha divided by sine of alpha. To do this, we're going to take one side of the equations only and try to get it to match the other side. So I'm going to take this side and try to get it to match the other side. So let's just start by rewriting things in terms of sine and cosine. Cosecant squared of alpha, how else can I write that? One over what? I think I heard somebody say it. Sine squared of alpha, but yes. Okay. Good start, which means that I have two sines multiplied in the denominator. What if I just split those apart so I can look at them separately? So I have 1 over sine of alpha times 1 over sine of alpha. Remember, my goal of this problem is to have a sine of alpha in the denominator, but I need one of them to go away. How can I make one of these go away? Can I rewrite it in some way? 1 over sine of alpha, I know we just redid this, is cosecant of alpha. And those two numbers, when they're multiplied together, is exactly what we want. Cosecant of alpha divided by sine of alpha. So once these two things match, you have verified that statement. If you get one side to reduce or simplify to equal the other side, you're done. Your work here is, or your answer is your work. For example 7, we're going to take this left side of the equation, we're going to make it to look like the right side. My immediate instinct is that there's nothing I can really do. Things are written in terms of sine and cosine. There's nothing I can split. There's no multiplication to do. There's no factoring. So I think about doing one of those conjugates. So what I'm going to do is I'm going to multiply the thing I've highlighted in red. I'm going to multiply it by the trig conjugate, 1 plus sine of x. When I do that, the denominator becomes a difference of two squares factor. If you remember your factoring rules, that means this is a super shortcut for you. 1 plus sine of x times 1 minus sine of x is just 1 minus sine squared of x. You can Google difference of two squares if you're like, what? That's too far back for me to go. Difference of two squares is what that's called. But the numerator, when I multiply that, cosine of x times 1 is cosine of x. Cosine, oh wait, I don't want to do that. Sorry, backing up. we're not actually going to multiply them. We're just going to stick them next to each other. Okay. The reason we multiplied by a trig conjugate is because now the denominator is one of my Pythagorean identities. What is 1 minus sine squared of x equal to? Cosine squared of x. Okay, that's simplified a little bit. That looks good. What do you notice might happen in this fraction? What's on both top and bottom here? Cosine. So let's cancel them out. So one of the cosines in the bottom cancels with the cosine in the top. Which means I have 1 plus sine of x divided by cosine of x. It still doesn't look like what I want it to look like, but if you notice, what I want it to look like is two separate things with no denominator underneath them. Is there a way I can separate this into two pieces? Because that plus or minus is in the top, not the bottom, I can actually separate this into 1 over cosine of x plus sine of x over cosine of x, giving the denominator to both. We're almost there, y'all. Is anybody's spidey senses tingling? Yes. About what?
1 over cosine.
What is 1 over cosine?
Secant.
Oh, snap. This is secant. Isn't that what we wanted?
Yes.
What else?
Tangent. Sine over cosine is tangent.
Sine over cosine is tangent using the quotient identity. So voila, this is what we wanted. We have verified that identity. I love these problems. It's like a puzzle. It's so fun. So much algebra, so little time. Now, last but not least, and to tie this back into what some of you asked me about the 3.10 lesson, solving equations, solving trig equations, we can now use these identities to continue to solve equations. So you just didn't have any problems before now that required the use of identities. But now it's totally possible because you have been aware of the different identities that exist. So in example 8, it says solve sine of 2 theta minus sine of theta equal to 0 for theta when theta is between 0 and 2 pi. So we're not writing a general equation here, we're just solving the problem. So let's take our statement, sine of 2 theta minus sine of theta equal to 0. We know from when we studied solving equations that we needed to probably factor this so it was one trig function equal to 0. Right now I have two trig functions happening, so let's see if we can reduce this using identities. On your formula chart, you have a formula for double angles of sine. What is that formula?
2 sine alpha cosine.
So we can rewrite that first little piece as 2 sine of theta cosine theta. That is using the double angle identity. That's the only new bit of this question. Now we go back to what we learned in 3.10. In 3.10, we still needed to get this where it was one trig function equal to either 0 or a number. So I noticed that both terms in this problem have a sine of theta attached to them, so I factor it out, which means I'd be left with 2 cosine of theta minus 1. At this point, once it's factored, you just set each of the little factors equal to 0. So you'd say sine of theta equal to 0 and 2 cosine of theta minus 1 equal to 0. Is this sounding familiar from 3.10? What are the angle measurements that sine is equal to 0 for? 0 and pi, very good. All right, so those are my two answers from that part of the equation. But I can't solve the second part yet until I isolate that cosine of theta. So I add 1 to both sides, divide by 2. What are the angles where cosine of theta would be equal to 1 over 2, 1/2? Pi over 3, and where else? Let me rephrase. What other quadrant? Because that's quadrant 1. Where else is cosine positive? Quadrant 4. So what's the quadrant 4 version of pi over 3? 5 pi over 3. Last question. I'll be honest, this one's kind of a doozy, so hang on, we got this. Number 9, using a sum identity. So there's your hint. Find all values of theta on 2 to 2 pi, where sine of theta plus pi over 3 is equal to 0. All right, hang on with me. Sine of theta plus pi over 3 equal to 0. It tells me to use the sum identity. So using that sum of sines identity from your formula chart, we know this left side can be written as sine of theta cosine of pi over 3 plus cosine of theta sine of pi over 3. All I've done is filled in for alpha and beta in the sum of sines, theta and pi over 3. For help, here's the color coding. So here's all right. So my spidey senses are saying, well, I actually know the value of cosine pi over 3 and sine of pi over 3. So let's go ahead and change those into that value. What is the cosine of pi over 3? 1/2. And what is the sine of pi over 3? Square root of 3 over 2. Okay, so that's nice. Just get rid of some of the trig here, have some values. I messed this up somehow. What did I do? Oh, this should be a sine. Sorry. And I don't love that there are fractions here. Is there something I can multiply everything by to get rid of the fractions? 2. I just like, since they both have a fraction, let's just get rid of it. By multiplying everything by 2, I end up with sine of theta plus square root 3 cosine of theta equal to 0. Now here's where this gets to be a doozy. Now this is an advanced question because there is no way for me to factor sine of theta and cosine of theta. They don't have a GCF. So we need to force them to have something in common. Let's force them to be tangent. What would I have to divide sine by to make it into tangent? Cosine, because sine over cosine is equal to tangent. So if I take this whole thing and I'm going to divide it by cosine of theta, that means my first term becomes tangent. What happens to the second part? The cosine's going to cancel, yeah? It'd just be plus square root of 3. And then 0 divided by cosine is still 0. That's our creative step here because there was no way to factor this, so we got them in terms of something we know using those identities. If I finish solving this problem, this is tangent of theta equal to negative square root 3. What are the angles where tangent is equal to negative square root 3?
2 pi over 3.
That's one of them. What's the other one? So that's from quadrant 2. The other place where tangent is negative is quadrant 4. So what's the quadrant 4 version of pi over 3? 5 pi over 3. So now You may not just see a regular equation for yourself to solve with trig. There will be identities tossed in that you're going to have to finagle to get it to be a problem you can solve. Don't break the rules, abide by the rules. All the rules are right there on that front page of these notes as a formula chart.